It's a pleasure to be here in Santa Barbara with all of you. Thanks for being here to hear my talk. So I know my title is pretty broad. So to give you an idea, I will be talking about kind of the basics of how we do quantum computing with trapped ions. And then I'll talk about a particular application that I think is a really nice example of how we can learn by doing and kind of find ways to make these applications possible and learn both about the experiment and how we can improve the algorithms. So in my title slide picture here, I have an ion trap chip. Oh, and please, if you have questions, I'm happy to take them during the talk. So this is our chip that we use to trap the ions. And in this camera image here, you can see we have a row of ytterbium ions in a chain, and these will serve as our qubits. And so I'll get into how that works. And most of the work that I'll talk about today was done at University of Maryland, but we've since moved to the new Duke Quantum Center. And so I'll tell you a little bit more about that as well. Just to start with what I think is a super cool image. So this picture was taken with a cell phone camera and a kind of a small microscope. And if you look with your eyes, you can also see this is a single barium atom that's fluorescing, and it's at 493 nanometers, which is right in the peak sensitivity of your eye. And this is just kind of a zoomed in version of this dot here. Now, what the point I want to make here is that these ions that we trap, they're surprisingly kind of these amazing quantum systems that we can control very well, we can see very clearly, and we can manipulate with lasers that you can buy kind of off the shelf. And so this is going to be our quantum system that we use to do computation and simulation. Question already.
That's a single barium atom, then what's that ring?
It's just an artifact of it's not a perfect imaging system, that's all. Okay, so just to give kind of another picture, we've been doing these ion simulations and computations for some time now, and these are just application examples that have been done at University of Maryland in the Monroe group in particular, and then also more recently in Norbert Linke's group, and so really just a rich array of physics that's possible with these well-controlled quantum systems. Now, those applications were at Maryland, and we are now moved down to the new Duke Quantum Center. So we have new lab spaces and many new faculty coming in. Our director of the center is Chris Monroe, who's really been a pioneer in the trapped ion field. And we have lots of young faculty as well coming in, having new groups, including myself. So we're just really excited about quantum at Duke, and we've got a lot of ions going on, some other atoms, and this is our first group photo from this year. So we are growing very quickly, and I hope that I can give you today kind of a flavor of what we're hoping to continue at Duke. So this is kind of a picture of where we are, where we're going. So this is our first system, which is the system that took the data that I'll talk about today. And you might recognize this picture from a certain report, but it is ours, not IonQ. So that's kind of the first system, and we've already iterated onto the next one where we've really modularized the system, kind of improved it in many ways. So we're hoping for some improved fidelities there, and we're now trapping in that system regularly. We also have been able to implement mid-circuit measurements, so we can go beyond just your typical single chain operation. We can split the chain in two and measure some of the qubits while the others are preserved. And with this capability, we're also kind of able to go into this new realm where in this video you can see we have a chain of ions and it gets split into actually 3 pieces. So we start here and there's 2, and then it gets split again, and then we can bring them back together. So the really cool thing about ions is that we can move them around in the trap. They're charged particles. We can push them around with electric fields. We can rearrange them, regroup them, So this really creates a different kind of modular architecture that we're going to start exploring in our next systems. And when you think about ion trapping, there are many different ions that people trap. They're generally from the second column here. And in the systems that I'll talk about today, we're trapping ytterbium. And in particular, we're using ytterbium-171, and the level diagram looks like this. So we have some transitions here. This one's used for cooling and detection. We have a narrow transition that can be used for some other synthetic cooling applications. The important thing is that we can buy lasers off the shelf and address these transitions, which is great. And our qubit is going to be in this ground state hyperfine manifold. So our spin down are 0 and our spin up are 1. We have this splitting here of 12.6 gigahertz. And this will be our qubit. This qubit is known as a clock qubit. It has extremely long coherence times. The T1 is essentially infinite. We don't even talk about it. And this is a measurement of T2 in our system with 15 ions with a microwave echo sequence, and we have a T2 of about 4 seconds. And with a similar measurement with our lasers is about half a second. So this is frankly something we don't think about that much. So as I mentioned before, we're trapping these single long chains of ions. And you can see in this picture that they're actually equally spaced in this chain. And we're able to do that by carefully controlling the potential that the ions are living in. And we can do that with these fantastic traps that come from Sandia National Laboratories. They have over 100 electrodes on them that allow this precise control of the potential. So this has really enabled us to be able to trap these long chains and control the exact placement of the ions and thereby control their motion, which is what we use for gates. And I'll get into that in a second. So I mentioned briefly already, our qubit detection is done with this 369 nanometer transition. So we shine in the laser light and collect the fluorescence, and we can threshold whether we see photons here, we're in the 1 state, and no photons, we're in 0. So we can do this with very high fidelity with even a small amount of the fluorescence detected. And in this system, we have a nice way of doing this where we have, it's a little hard to see in this resolution, but there's actually many fiber cores lined up next to each other in an array here. So each ion is lined up on top of its own fiber that guides the light into its individual detector. So we have very little detection crosstalk in this system. So the next thing we like to do is, of course, manipulate the qubit, and we do that using a 2-photon Raman process. It's detuned from this excited P state here, and we can do that using an off-the-shelf coherent laser. It's a pulse laser that we modify slightly to control the rep rate. And so using this laser, we can do all of our coherent qubit operations. And since we're working in a long chain, I just wanted to give you an idea of how we work with these ions in terms of their motion and how we can make gates. And so if you think about something as simple as a guitar string, right? We have this harmonic oscillator type modes. Our ions are going to be exactly like this in the chain. They're just a bunch of coupled harmonic oscillators. And so we can look at the spectrum of the modes that we get from such a system, and we have some low energy axial modes that are along the axis of the chain, so the ions are moving together. And then we have the transverse modes that move perpendicular to that axis. And so by tuning our laser near these modes, we can create the interactions kind of using that motion as a quantum bus. So what that looks like in a long chain, if you illuminate the entire chain, and so in this example, this is a crystal of 121 ytterbium ions, you can illuminate the whole chain, and what you get is this long-range Ising interaction. And you can tune this, the range of that interaction by changing, by exactly tuning the potential and tuning the modes of motion. And so there's just a wide variety of rich physics you can do with this. You can, of course, add transverse fields, and this has been a very fruitful part of ion simulations. I just have a couple of examples from the Monroe group here. However, in our system, we're interested in specifically 2-qubit interactions, so we can make 2-qubit gates. And the way we do that is we have one beam that does address the entire chain, but then the second beam for the Raman process, each ion gets its own beam that we can control the frequency, phase, and amplitude of individually. And so we can choose any two ions in the chain, turn on their beams, and thereby create an interaction between them. And so in this way of doing it, we actually really excite the motion of the chain, but in the end, we can ensure that we're left with a spin-spin interaction, or this Molmor-Sorensen interaction, which is our native operation in XX. And it's got a couple of important features I just want to point out. The first is that this angle of the XX is variable. So we can, that doesn't have to be a fully entangling gate, so if you wanted to make a C0. And the second thing is that we can do XX or YY or anything in between. So we also have that tunability. Yes?
So you can control the gate from an interaction between any two ions. Is there some low probability that this could happen spontaneously? And should I think of this platform as having k local modes?
No. So only in the sense that, okay. So the spins only participate in this interaction if they have a laser light on them. And so the only way that that happens is if you have a beam that leaks over onto its neighbor. The ions that are maybe on this end of the chain in this picture, where I've chosen these two ions, they have no entanglement with the motion. Okay, and as I said, you can choose any two ions in the chain to entangle, and so we effectively have a all-to-all connectivity in our system. So I keep calling it a system, and I think from somebody who has worked on AMO experiments, I just want to point out that this is we're really approaching this as a systems engineering problem. So we are working in things like automatic control, where we can load up our chain of however many qubits you like. So we load over here on the trap and then shuttle the ion into the middle region where it gets merged into the chain, like in this video. And we use all Python-based control with like community open source code that we can all work together on, and this has accelerated what we do quite a bit. And then we also work very closely with our industry partners on this project. So when it comes to something like the Raman system that does all of our gates, that's actually all the engineering, the optical engineering there was done by the team at L3 Harris. So we've taken what really is the most important part of our system that we get right, and we've given it to the professionals. And that has made a huge difference in what is possible in the system. Okay, so this is kind of a summary picture of how our operations are in the system. And of course, this is from a year ago now, since before we moved. So big caveat on all this. But so we typically are working with 13 qubits. It's a 15 ion chain with 13 usable qubits. All-to-all connectivity. Those XX gates are typically around 99%, and our single qubit gate fidelity over 99.9. And then we have some small spam. So this is the picture of the system that we're going to be working with and the data I'm about to talk about. So this would be a good place to stop for questions, actually.
So I had a couple of questions about this Molmor-Sorensen gate. On the one hand, do you have to calibrate for specific angles in order to optimize fidelity, or do you have sort of angle-dependent fidelities?
To first order, no. To first order, we can scale the amplitude of the gate to set the angle. So second order, there are some subtle phase issues that we do have to calibrate when you change the angle. But I'd say that's not, we haven't necessarily explored that in terms of the actual fidelity.
Okay, gotcha. And then, so second question. If you're entangling two ions, say at the two ends of the chain, do you have to let that interaction run for a longer amount of time for it to accumulate the relative interaction?
No, so the kind of relative position in the chain is not the important question. It's the participation in the motion. So for example, there's a mode of motion where the chain is tilting back and forth. And so the ions on the end participate a lot in that mode. So they can be coupled very quickly. Whereas if you tried to use that mode with the center ion that doesn't move at all, then this would not work.
Great, thank you.
I just had a question about the mid-circuit measurements. When you split the chains, like, do you have like other ions to like cool back to the ground state sympathetically?
That's a good question. So no, when we've been doing it recently, but we also did not attempt any 2-qubit gates after those mid-circuit measurements for exactly that reason. But we're also have some results on adding sympathetic coolants, so that's.
Is that the long-term vision for that?
It's like the next month vision. Cool. Yeah. Okay, I will keep going then. Great, so I'm going to talk about a particular application that we worked on recently that I think is a really nice example of how we can learn by working on this system. So in particular, we're interested in simulation of NMR experiments. So in an NMR experiment, you have some molecule. In this particular example, you could say it's a liquid state. There's also a solid state NMR. And you take this molecule and you can put it in a magnetic field and then do kind of a Ramsey sequence where you look at the spin evolution over time. And depending on, then you take that evolution, take a Fourier transform, and you're left with a spectrum. And by looking at the spectrum, you can figure out the structure of the molecule. You can see in this example where I labeled what the different peaks correspond to in terms of the different hydrogen atoms. And this evolution is of course determined by the Hamiltonian, and it's a simple spin-spin interaction, and then some kind of magnetic field term. And so by looking at this spectrum, you can, kind of all of these things go together, right? If you know the structure, you can know the Hamiltonian and the spectrum. But now what we'd like to do is think about this idea of NMR inference. So let's say instead of having a molecule that I know, I have an unknown molecule in my sample, and I get some complicated spectrum out. And then the question is, what molecule do I have? And so what we'll do is take this basic Hamiltonian and simulate it, and then work in these cycles where we vary the parameters until we get a good match on the spectrum. And then once we do that, we can say that we know what the molecule is. Okay, so where does quantum come in? Well, when your molecule starts to get really big, so in this example, this is 34 spins, this is already at the limit of what the classical simulation capabilities can do. And so the idea here is we replace this classical simulation with a quantum one, and then we do a classical optimization of these Hamiltonian parameters in order to infer the structure of that molecule. Okay, so that's kind of the larger vision of this, but of course we can't start with 34 spins, let's start with something smaller. And so the molecule that we look out here is acetonitrile. So it has this methyl group with the 3 hydrogen spins and then a carbon 13 spin. And so the Hamiltonian looks like this. And in this case, we're going to look at 0 field, so there's no magnetic field term. Okay, so now we have our Hamiltonian, and what we'll do is we'll assign 1 qubit per spin, and then evolve under this Hamiltonian, and then take a Fourier transform, just like in the NMR experiment, but we're going to do it with our quantum simulator. So the way that we do this is actually using, and so you could say, okay, well, if I could just make a atomic system that does exactly this interaction, then I could just evolve it and then read out the magnetization directly, sort of an analog approach. But it turns out getting, this is XX, YY, and ZZ terms, and in general, you only get kind of one or the other, right? So doing both is actually pretty difficult. As I mentioned, our native interaction is XX, YY, but doing also ZZ is actually pretty hard. So instead, we take a digital approach to this. And so what we do is we take each time step of this evolution and we turn it into a circuit. And in particular, we use an algorithm that can compile these circuits and optimize them. One important, and so they look something like this. We have our 4 qubits. They get initialized in some initial state, and we have 8 of those in particular, and then we can do the evolution for each one and then take an average. And this is an example of what the circuit looks like, and you'll see this compilation of the circuit takes advantage of the fact that these MS gates, this is our XX gate, can have this variable angle. So we're not limited to C0 or anything like that. We can take advantage of this kind of tunability of our platform. Right, so this ended up being a really important part of how we could get these circuits down to a depth that was reasonable. And then the second thing that we added in order to do the simulation is compressed sensing. And the way this works is we know that our spectrum that we're trying to recreate is very sparse. And so we don't actually have to sample very densely in the time domain. We can undersample and still recover enough information. And so what I'm showing here is this free induction decay, in other words, this time evolution over time. And we have on the line is a noisy emulation of the circuits. So we take kind of our known noise parameters and simulate these circuits. There are only 4 qubits. We can do this. And then the trapped ion data, the data on our quantum simulator are the dots here. And so you can see how few points we actually take with this compressed sensing. So this was a huge reduction in the amount of data that was required. And this is only showing out to 0.2 seconds. We actually went all the way out to 6. But this kind of time of the time evolution no longer corresponds to a sense of experimental time, right? Because we're not doing this in an analog way. So, the length of time of the evolution has nothing to do with the circuit depth anymore. Okay, so this is what the data look like, and then you take a Fourier transform, and this is what we get. So if you can see the lighter color here is the actual NMR experiment that was done on this molecule, and then the darker color is our quantum simulation. And so we're able to reconstruct the spectrum with an uncertainty in other words, the width of these peaks of less than 0.1 hertz. And this is quantitatively actually better than the experiment, like the actual NMR experiment. So we're able to very well quantitatively determine where these peaks are. And we also observe this extra peak here at J/2. And this is actually really interesting story that I don't have time to get into, but this is something we did not expect to see, but it turns out it makes complete sense when you look at the molecule that we're simulating. It has this symmetry to it, and so there's a interesting story of how this J/2 peak falls out of it, and we now know what to look for and how to account for this as we scale up to larger and larger molecule sizes. So that's available in the paper on the archive if you're interested in that story. I guess I could also answer questions. Okay, so now the question is how do we scale to larger molecules? And I just want to point out that we're at this conference about applications and advantage in these NIST devices. And what's really cool about these NMR simulations is that we're not necessarily interested in the exact unitary simulation. What we're interested in is the spectral resolution. And as long as we can meet the spectral resolution of the experiments, then we can do something useful. And these NMR systems, when you have something that's in the liquid state, for example, they naturally are already dephasing, and so the requirements on this are not so strict. And so we looked at this more closely So this is, again, this 34-spin molecule, and this is just kind of estimating the resources that we would need in order to simulate this. And so I can walk you through this plot. So on the y-axis is the resolution, where about 1 hertz is what NMR experiments usually get. And then on this axis, we have the circuit depth. And so if we take a particular fidelity of our 2-qubit gate, each of these curves tells us the achievable resolution, where, you know, if you go too deep at a certain fidelity, of course, those errors just from your gates take over. But there is some kind of optimal resolution that you can achieve. And so in this case, we show that with 4 nines of fidelity in our 2-qubit gate, which has been done in ion trap systems, just not at this scale, obviously, then we can start to already do something with this problem. Because as I mentioned, this 34-spin molecule is already at the edge of what can be classically simulated. Okay. So then I just wanted to kind of take this one step further and say this is one example, and I think just my personal opinion on where I think we could really do something cool. Definitely with, you know, quantum dynamics, this time evolution is a really hard problem to simulate, especially with many body systems. So I think this is somewhere where I think we'll get there quickly. This is an example with ions. Also in strongly correlated systems, right? So when we have lots and lots of entanglement, this is an example of quantum spin liquid and atoms, and then also in quantum chemistry, and these are examples in superconducting qubits. So I think there's lots of ways that we can go in all these different paths to reach some kind of useful application. I just want to also mention that, you know, we have this system that I've talked about, and we've been able to maybe do what John Martinez would not be a fan of, but we're enjoying ourselves exploring all of these applications and publishing in Nature. So, you know, we've looked at measurement-induced phase transitions, verification protocols, classical shadows, and also some work in error correction space. And I just want to say that, you know, similar to the NMR experiment, we learned kind of a new way of doing these things, not only on the hardware, but also in the application itself, by going through this process of actually implementing it on the hardware. And it definitely pushes our limits of what's possible. So, for example, this, you know, both the error correction and this interactive protocols required this mid-circuit measurement, and that pushed us to do that in our hardware faster than we might have otherwise. So it's a really exciting time to be working on these systems. I also just want to put in a plug, since I am a new assistant professor. So I'm going to be working at Duke not only on these systems and applications, but also thinking more about the devices. Actually, I feel like I'm justified because my PhD was actually in noise. So I've now been on both sides of this coin. And so I'm continuing some of these noise investigations in ion traps, thinking about new materials and integrated photonics, and how we can really scale these systems up to many, many qubits. So I have many people to thank. Of course, our PI in these projects is Chris Monroe, who's now the director at the Duke Quantum Center. And this is just the experimental team that worked on NMR simulation in particular, and we have some fantastic theory collaborators, in particular Kushal, who works with Eugene and Dries, and of course our funding agencies. And thank you for your attention.
Very nice talk, thank you. I had a question about the NMR part. Maybe I misunderstood something, but the way you motivated kind of this line of work is that you might have a mystery molecule that you don't know about and you want to find out about. So I'm trying to understand how the trapped ion simulation would work. Would you do an experiment on the NMR side and then have trial Hamiltonians? Because presumably you don't know your Hamiltonian, right?
Well, we know the form that it should take, because these NMR experiments are probing the spins in the molecule.
Right, but so, I thought you said you don't know what kind of molecule you have.
Right, so we don't know, let me go back to that slide. Yeah, so we don't know these JIJ terms, so the coupling between any pair of spins, but we know that we're looking at spin-spin interactions. And so there, depending how many spins you have, there's many of these terms that you have to figure out.
But do you know how many atoms your molecule has and what it consists of?
That's a good question. Yeah, so I'm not sure. So I guess you probably know something from the spectrum that you have, like that tells you about the complexity. And I think also you probably don't start with something that's completely mysterious, right? So I mentioned liquid state, but we also more recently I've been thinking about like solid state, and you usually have like some kind of polymer or something that you're interested in, and you know the basic structure, but you're not sure exactly how all the atoms are arranged. So I think you have to start with something. Yeah. That's a good question.
So thanks again for the great talk. I'm curious, when you get to something like a 34 spin molecule, and you're trying to fit these H and J parameters, that becomes a pretty difficult optimization problem in general. Do you all have techniques that you've looked at for trying to perform that at scale?
I mean, I specifically no, but it's like any other classical optimization problem. I don't know what the landscape looks like, which is like kind of what you're asking, but yeah, that's a question for NMR folks.
Thanks.
I'll just say to the previous question about what you would know about, based on a spectrum, trying to figure out the structure of the molecule. Just based on having done some NMR spectroscopy in my life before, typically what you would see is from a spectrum, you'd be able to read off some what's called functional groups of a molecule, which are just well-known structures that have signatures. And so the rest of the problem becomes sort of fitting them together on a molecule to know sort of where they fit together. And in this sense, it could be useful to be able to sort of optimize and see how those functional groups would fit together. So,
thank you. Yeah.
Thanks. This is probably a very simple-minded question, but for NMR, I might think that hyperfine couplings would be important, and they're not anywhere in the digital simulation, right?
I don't know.
I mean,
I don't know the answer
you're
to
writing
that.
down a Hamiltonian, which is supposed to describe only the nuclear spins. If there's any
Yeah.
other degrees of freedom that matter, like coupling to electron spins or anything else, then that's...
So I guess one thing I do know is you do end up with like dipole-dipole terms, but if depending, so in the liquid state, they do just kind of average out. In the solid state, I don't know as much about that. But yeah, that's why in this case we don't have that term.
I'm again interested in like the transport you guys have in mind. So do you imagine just being able to like split and linearly move the chains, or can you like shuffle the ions within the chain, or you're just thinking of doing that with the gates anyway?
So it is possible to physically, so I've shown everything kind of in this 1D architecture, but they do exist in 3D, and it is possible, and it's been shown by groups at Innsbruck and also I believe at Mainz, where they can actually swap in space two ions physically. And this will be, in general, a higher fidelity operation than doing a gate.
Yeah, I just imagine it's hard to do the swap well with like more than two.
Yeah, you have to do like 2 at a time, basically. And we've done this in our system for purposes of being able to reorder the chain in situ. And so yeah, it's totally possible. Now I'm in the kind of next architecture we're envisioning. I'm not necessarily sure how much of that we would be doing, because I think we're more thinking about having, when you have these long chains, what's great is you have all-to-all connectivity. And so rather than thinking about really just moving ions around all the time, which is kind of the continuum approach, instead having these long chains and maybe bringing them together or bringing pieces of them together to create new long chains, to take advantage of that. Yeah, but there's like so many ways you could go. That's what makes.
Yeah, I'm just wondering what do you have on the short-term plans?
Yeah, so in the short term, we are thinking about this kind of reordering problem, because once you add coolant ions that are a different species, if the chain reorders and now your qubits and your coolants are in different order, this can cause problems for your gates. So we have to think about how to put them back in order. So that's in the very near term. And then I think the next system will take some time to come to fruition, but we'll see when we get there. Yeah.
You mentioned a difference in frequency resolution between your experiments and NMR. Can I interpret that as being some statement about the differing coherence times for the spinful degrees of freedom in your experiment and in an NMR experiment, measured in terms of the interaction time or something like that?
Yeah, at these scales, that's not really part of the equation.
Okay.
It just comes down to the high fidelity gates that we're doing.
So actually, your experimental runs, how many interaction times do you tend to go to in order to generate these?
So the biggest circuits, I believe, had about 60 gates, okay. Which is what is that? And our gates are 200 microseconds. So that's nowhere near our 600 millisecond T2 time.
Okay. Thank you.
Coming back to the circuits, they looked nothing like Trotter evolution, and I think this is what you wanted to emphasize. So if you did do Trotter evolution, like how significantly different would they be in size? Because presumably in Trotter also you can use.
Let's put it this way: we tried that approach in theory and did some tests, and did not go any further because they were prohibitively long. We could not get enough time evolution to get a meaningful spectrum. It just wasn't going to work.
Cool.
Question.
Hi, thanks for the very nice talk. Could you go back to the slide with the circuit on it?
Yeah.
So is the alignment meant to imply that you're doing gates in parallel, like those layers of RX gates?
So no. Right now, all of our gates are in series. So this is not meant to imply.
So you just lined them up there just kind of for ease of organization?
Right. Yeah.
Okay.
If I put them all in sequence, you wouldn't even see this one on the screen.
Okay.
That's all.
Thank you.
But yeah, we do our gates sequentially currently. It turns out when you start doing gates in parallel on ions, because they're all participating in the motion, it becomes more and more complex to complete the gate that you intended. And so have been some attempts to do parallel gates, but they were worse than doing them sequentially. And so we just go with that. And the same goes for these. When you do these single qubit gates, you can create basically XX interactions on accident if you do them in parallel. So it requires even more design of those gates. It's possible, definitely possible, but it's not something we need to do at these fidelities.
So this is kind of a difference between your approach and how you would do it on a superconducting machine where you try to run a bunch of gates in parallel.
Yeah, I mean, we're not fighting short coherence times, so the cost of doing them sequentially is not so high.
Okay, thanks.
I have one more question about your basic apparatus and stuff. So your readout error was something like in the 0.3% range, but that's presumably for each ion, right? So, like, I guess my question is, what's like a strategy you would use to improve this? Like, is it fundamentally limited by something or no?
No, not at all. We made no effort to improve this. 0.5% is basically we couple to the fibers and everything is well aligned, and that's what we get. There are a myriad of ways to improve this. In ions, I'm going to get this wrong. I want to say the latest result was over 4 nines of detection fidelity in ytterbium. And so, yeah, there's many ways to make this better. Most of it involves kind of shelving information in dark states so that you can read out more safely. But yeah, no, this is no effort, really.
Okay, thanks.
I mean, there was effort in the design, right? Like choosing this fiber cores, the way that we did it. But we actually have a pretty small NA on this system. Like, it's really not built for collecting photons.
The fact that you can write down the circuits which do not look like Trotter and are much shorter, is it based on the fact that you can simulate the whole dynamics of your molecule with a classic computer, or?
No, I don't think this compilation algorithm relies on the fact that you can simulate them.
Okay, so you could like scale this up to, I don't know, 40 qubits and still sort of.
Right. Yeah.
Okay.
Yeah.
Okay, if there's no more questions, let's thank Crystal again.